on page 19 of our notepad, and we were just practicing this problem, recognizing the functional groups. And this brings us back to all of the functional groups we've been practicing. I have a list here, A through letter E on page 19, and you've paused your video by now and have had a chance to work through. And this is just an opportunity to check your work. So in letter A, what I just noticed here is a C double bond C, and the functional group we're learning is called an alkene. In letter B, I notice we have a functional group. This is called an alcohol. And here we have a cycloalkane. In terms of the carbon chain is in a cyclic structure, so we can go ahead and practice naming that as well as a cycloalkane. Here I have a carbon double bonded to an oxygen. That carbon is bonded to two other carbons, so we call that, in terms of our functional group, this is known as a ketone. We also have a cycloalkane in letter C as well, in a 5-membered ring. The next one I notice I have a carbon that's bonded to a hydrogen that's also bonded to an oxygen. Carbon requires 4 bonds, so we also know that CHO is a carbonyl group. At the terminal end, this is known as an aldehyde. The carbon attached to the double bonded oxygen is a cycloalkane. And again, a 6-membered ring we'll learn is called cyclohexane, and an aldehyde at the terminal end. In this particular letter, I notice we see a functional group CO2H. We have to recognize that the carbon is double bonded to an oxygen and then leading out to an hydroxyl group, an OH. This is what we refer to as a carboxylic acid. The R group, this carbon chain, is an alkane since they are all single bonds. Letter C looks familiar from a previous example, except this is a 6-membered ring instead of a 5. We called this a ketone. The carbonyl carbon leading out to the double bonded oxygen is in a cycloalkane and leading out to the ketone functional group. Now notice here, I notice some oxygen. Just kind of bringing that together, I have a carbon, 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 1, 2, 3. Carbon 3 is double bonded to an oxygen, leading out to another oxygen. That's why we see it written as CO2. And then we have 2 more carbons in that chain. This is what we refer to as an ester. And finally, I have a carbonyl carbon directly attached to a nitrogen, and that functional group is known as an amide. And this is what we refer to as a cycloalkane. Here we have a 5-membered ring, so we will learn to call it cyclopentane, attached to an amide functional group. Is this an ether or a ketone? On the top of page 20, we have more practices recognizing the way that we write an ether versus a ketone. In letter A, I have 2 groups of methyl. So what that looks like when I write that out, I have the oxygen, and on either sides of that, I have a methyl group. So that is ROR. This is what we refer to as an ether. Here I have CO, so the double bonded oxygen, and leading out in either direction is the methyl group, a CH3 on either side of the carbonyl carbon. This, by definition, is a ketone because of the carbonyl carbon. Letter C, I again recognize a CO, so that means that there's the C double bond O. And on either side, I have a CH2, CH3. So since they're the same group, we've written that in a condensed form. CH3, CH2 taken twice, CO, represents a functional group of a ketone. And notice here the oxygen is coming after the hydrogen here. So I have a carbon, CH3, carbon, CH2, and then an oxygen. And then I'm having a carbon leading out to a hydrogen and 2 groups of CH3. So there's its structural formula for letter D, seeing that oxygen is indeed part of the backbone. We call this an ether. So drawing those structural formulas out helps us to see the connectivity to properly identify an ether, which is ROR, or a ketone, which is RC double bond OR. And identify all functional groups. And I encourage you, practice this first before we talk it through, practicing on your own paper and then come back to check when ready. Okay, so how did you do? Well, I'm just going to jump in and say one thing I noticed right away is the double bond. So I need to label that as an alkene, E-N-E, because it's a double bond. Here I'm noticing a CO2. So remember, carbon double bonded to an oxygen, leading out to another oxygen, and then it looks like 2 more carbons at the end. So this is our functional group known as an ester. Here we have a nitrogen coming back attached to a carbon that's attached to other carbon. So this is an amine. Here I have a carbonyl carbon directly attached to the nitrogen. So this entire functional group is known as an amide. And here I have an oxygen directly attached to 2 other carbons, and that makes this the ether. Just like the previous slide we're practicing. And that, I think, recognizes all of those functional groups within that compound. And this, again, is just kind of a neater slide to make us realize we had a double bond alkene, we had an ester, amine, amide, and an ether, highlighted for neatness so you can check. In our next topic, we talk about properties of organic compounds. Properties of organic compounds in terms of polarity. So organic compounds are composed, we know, of covalent bonds only. There are no ionic bonds. These organic compounds exist as discrete molecules and form these intermolecular forces or intermolecular attractions between molecules, which are weaker than we see in ionic compounds. So as a result, organic compounds typically have lower boiling points and melting points than ionic compounds. Remember, ionic compounds are commonly called salts, and we see those as solids at room temperature, whereas organic compounds tend to be liquids and gases at room temperature. When we compare physical qualities of ionic compounds, think of a table salt as an example, a solid compound with a repeating crystalline structure. And in terms of organic compounds, this is lighter fluid, if you will, in a side of a lighter here. And lighter fluid is called butane. And butane is a 4-carbon chain, an alkane functional group. Alkane, in terms of a butane, is a liquid at room temperature. And you can see just discrete molecules that are separated in terms of distribution inside of that container. A covalent bond is nonpolar when 2 atoms of identical or similar electronegativity values are bonded together. So we'll need to remember specifically 2 nonpolar bonds are carbon to carbon and a carbon to hydrogen. Both of those are considered nonpolar based on electronegativity difference being so small. A covalent bond is polar when atoms of different electronegativities are bonded. One atom in the polar bond is much more electronegative, meaning that it can pull the electron density towards itself, giving itself a partial negative charge. And the more a more electronegative charge, the more electronegative element pulling its density toward there gives it a negative charge. And we would read this as a little Greek symbol, reading as partial negative. Carbon, which is less electronegative, remains a little bit partially positive in this bond. You might also see this written in general chemistry with a polarity bond, where we have an arrow with a tail that looks like a little positive sign leading to the more electronegative. Now remember, on your periodic table, fluorine is the most electronegative. Right next door to that is oxygen, right next door to that is nitrogen, and then carbon. Fluorine, chlorine, bromine, iodine going down in group 7A. Electronegativity increases as you approach fluorine in both directions. So fluorine is the most electronegative, meaning it has the ability to pull electrons towards itself in a shared pair. So a covalent bond that's being shared by an electronegative element is considered to be polar. So let's practice. Identify all polar bonds in each of the compounds and label them with their distribution of charge. Here we have a central atom, carbon, and carbon to hydrogen is nonpolar. And that's one that we're working to memorize, that CC or CH bonds are nonpolar. Remember, these electron-rich chlorines all have these electrons outside of the chlorines here, just to kind of finish those up, meaning that the electron density is being pulled away from the carbon towards each of these chlorines. So the electron distribution is being pulled away from carbon toward chlorine. There are 3 polar bonds in this structure. They're all identical. They're all C to Cl, and the bond distribution is being pulled to the electron-rich chlorine. In letter B, here's a molecule called formaldehyde. Of course, the carbon to hydrogen bond here is nonpolar, so we don't talk about it, but we see that carbon to oxygen is a polar bond, making this a very rich electron area on the oxygen, and making the carbon electron deficient, giving it a partial positive. I should do that up here as well. I'm going to add partial negative signs to the chlorines and reminding you that the partial positive is on the carbon, since the electron distribution is being pulled away from the central atom. And in letter C, I have a polar bond between the carbon to fluorine, with the electron distribution being pulled up toward each of these fluorine. So here's a second polar bond, making these very rich in electron density, and this carbon is electron deficient, so it's partially positive. Here's yet another polar bond. Let me change color. The carbon to oxygen is a polar bond, so again, making the oxygen very rich, negatively charged. This carbon would also have a pull towards the oxygen, making it partial positive. And I'll go back to red because this is a symmetrical molecule. We'll have pulls of electron density towards each of the fluorine, as well as each to that chlorine, making fluorines rich in electron density. Chlorine would be rich in electron density, leaving the carbons electron deficient with partial positive charges. So all kinds of polar bonds in that particular molecule. The only non-polar bonds there are represented by carbon to hydrogen bonds. In terms of polarity, hydrocarbons that only contain carbon to carbon bonds or carbon to hydrogen bonds are said to be non-polar molecules. So the entire region is very equal in electron distribution. There's no interesting area, if you will, in the molecule. So when you think of non-polar, think of an equal electron distribution, a totally symmetrical looking molecule. So here, carbon to hydrogens, carbon to carbon, all of these are non-polar bonds. making a non-polar molecule. But now all of a sudden, if we have a single bond that is polar, it makes the entire molecule polar as well, as it contains what we refer to as a net dipole. The net dipole means that there is an unequal distribution of electrons throughout that molecule. An unequal distribution. And so when I draw chloroethane, the first carbon contains all nonpolar bonds as it leads to three hydrogens and to another carbon. Of course, the carbon to hydrogen bond here is also nonpolar. But then all of a sudden we have something a little more interesting. The carbon to chlorine is a polar bond, making the chlorine very electron rich since it's more electronegative, making the carbon electron deficient, leaving it with a partial positive charge. So this area of the molecule is very electron rich compared to the nonpolar side of the CH3. So overall, the molecule is polar, as well as one of the polar bonds. If the individual polar bonds, which we can call dipoles, remember what a dipole is? Think of a bar magnet. A bar magnet which has a positive terminal and a negative terminal. It's considered a dipole because it has two charged ends that are oppositely charged, a dipole. So when we're looking at a molecule, let's say when I drew that carbon to chlorine bond, and it had a positive region and a negative region, this could be thought of as a dipole. It has a dipole moment, which means an unequal distribution of electron density throughout its structure. If we have a perfectly symmetrical molecule and the dipoles cancel one another, the molecule actually ends up to be nonpolar. So let's take a look at C2, Cl2, dichloroacetylene. Even though this carbon to chlorine is a polar bond, noticing that the electron density is being pulled towards the chlorine, it's being pulled equal but opposite directions, creating an equal distribution of charge overall. It's a perfectly symmetrical molecule. This carbon to carbon triple bond is nonpolar, but the bonds leading out to the chlorines are indeed polar, but since they're equal distribution, the molecule itself ends up to be nonpolar. However, if we have two dipoles that are not canceling, the molecule can end up to be polar. Here we have a central oxygen and a polar bond leading the electron density towards that oxygen, making this region very electron rich and leaving both ends electron deficient, which would create positive charge. This is an unequal distribution of charge, making this molecule very rich in negative charges up here, but very deficient in electric charge down here. So this ends up to be a polar molecule. Notice that the oxygen has 4 domains. In other words, 2 are bonded to atoms, but 2 remain as lone pairs. Since they are not all identical, it is not symmetrical, and therefore you know that it is a polar molecule. Explain why CH2Cl2 is a polar molecule. Well, let's draw the 3D structure to help examine the answer to this question. Notice that the central atom will be carbon. Carbon has 4 bonds. 2 of those bonds lie in the same plane. One of them will need to be a wedge, and the 4th will need to be a dash. And it does not matter which way we set these up, but I'll model what you see on the page here. The carbon is attached to 2 hydrogen and also attached to 2 chlorines. Notice that the chlorines also contain 3 sets of lone pair electrons. The carbon to hydrogen is nonpolar, but the carbon to chlorine is indeed polar. So there is a net pull of electron density out of this molecule, making this a very electron-rich area, and this region a very electron-deficient area. CH2Cl2 is a polar molecule simply because the bond dipoles do not cancel. It creates a very rich electron area with an unequal distribution of electron charge. Thinking symmetry, if your central atom carbon is attached to 4 identical atoms, it will be nonpolar. If I had chlorine attached to all 4 bonds, it would be a nonpolar molecule since all distribution of electrons are equal in all directions from the carbon. But if I simply take off one of those chlorines and put on a hydrogen, say, now it's not symmetrical in all directions. This becomes a polar molecule with a very electron-rich region over here and electron-deficient region on the hydrogen. So as you're practicing polarity, simply decide if the molecule has something interesting, a polar bond, and if it does so, are they creating an unequal distribution of charge? For example, cyclopropane contains all nonpolar bonds. I see that all the bonds are either a carbon to carbon or a carbon to hydrogen. And so therefore, there's not any polar bonds. Therefore, the molecule must be nonpolar. In letter B, I notice a polar bond right off the bat where carbon and double bonded to oxygen create a very rich electron area on the oxygen, leaving this carbon electron deficient, partially positive. Because it's an unequal distribution of charge, it is a polar molecule. Letter C, I drew just a moment ago, carbon tetrachloride. And since all of the chlorines are exactly the same in all 4 directions from that particular central atom carbon, there's nothing unique about the structure in any particular direction. It's perfectly symmetrical, meaning it's an equal distribution, so nonpolar. Here's letter D. I have a CH3 group, all nonpolar bonds, attached to a CH2 group, all nonpolar bonds, attached to yet another CH2 group, so that's all nonpolar, and finally something interesting, an NH2 group, where I can see that I have a polar bond leading from a carbon to nitrogen and from a hydrogen to nitrogen, making this region very electron rich, and these hydrogens, as well as the carbon, electron deficient, so they're partially positive, making this a polar molecule. In terms of solubility, the general rule is likes dissolve likes. So likes dissolve likes simply tells us that polar will dissolve in polar molecules, nonpolar will dissolve in nonpolar molecules, but never the two shall mix. Polar with polar, nonpolar with nonpolar. So that means most organic compounds are soluble in organic solvents. Hydrocarbons and other nonpolar organic compounds will be insoluble in water. Polar organic compounds are water soluble only if they contain a small chain and either a nitrogen or oxygen to help with the polarity so it can form hydrogen bonds with the water. So let's review what we've said. Likes dissolve likes. Here we have 1, 2, 3, 4, 5, 6 carbon chain. It's all single bonds, so we know it's an alkane. 1, 2, 3, 4, 5, 6 would be its line structure. This is a non-polar molecule because every single bond is non-polar. Would this be water soluble? Well, water, we know, is highly polar. I don't mean that to have up. So water, we know, is highly polar based on its bent molecular geometry, a very electron-rich region on the oxygen, electron-deficient regions on the hydrogen, with the dipole moment being pulled towards that oxygen. So water is a very polar molecule. If hexane is nonpolar and water is very polar, those two do not form a solution. They are said to be immiscible. They do not mix. Here on this example, we have a 2-carbon chain with the alcohol functional group. We know that alcohol, OH, is a very polar region, meaning that the electron density is being pulled towards the oxygen, making it a very rich area. Since this is a small polar molecule, polar with polar will be soluble. We call this a miscible solution. They do blend together. Here we have a molecule called cholesterol, and it's a very large molecule, isn't it? The large molecule of ethanol makes it, of cholesterol, makes it so large, so heavy, that it is actually insoluble in water. Now notice that I find some polar regions. I have an alcohol group down here, and I know that that's polar, but I want us to also know that this entire region is made up of carbon to hydrogens, which is all non-polar, and certainly this is a much larger region, so it will dominate for physical properties. So overall, even though there's this tiny little polar region, this dominates non-polar to be an insoluble solution. Cholesterol does not dissolve in water. Are these water soluble? Write down yes or no, and then come back to practice. Letter A is octane. It is an 8-carbon chain where each one of the line structure bends represents a carbon. This is a non-polar molecule. So does it form a water solution? No. Here we have acetone with a very electron-rich oxygen area, an electron-deficient carbon area. So this is a polar region, and it's small. So yes, I would predict this forms a solution. And down here we have a fatty acid called stearic acid. And my eyes first went to this functional group for a carboxylic acid, COOH. The carboxylic acid is its functional group. And clearly, that looks like a polar region. However, how many hydrogens and carbons are attached to that polar region? We have 16 plus one more, 17 carbons attached to that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then here is finally the COOH. This by far is a non-polar region. Even though there's this tiny little end that's polar, the domination of the non-polar region makes this a non-polar molecule. And so no, it's too big. Even though there's a polar bond there, it's too big to be water soluble. What you have left to do involves reading through your textbook. This is your assigned reading, and it's going to focus on health and medicine in terms of vitamins being water soluble or fat soluble. So page 24 of your note pack is yours to finish up using your textbook. And remember, once this note pack is completed, you will convert it into one single document. using your CAM Scanner app on your smart device. One document. Please do not upload any more than just one document that's multiple pages long. Review how to use your CAM Scanner app so you receive credit on your homework here. I look forward to getting your note packs very soon.